Next, we have Associate Professor of Chemistry, Dr. Dean Kirby, presenting on Gibbs free energy.
Before I start, I have to say this. The only time I've seen so many people in this room was two occasions. One was an Ash Wednesday Mass, and the other was when a Nobel Prize winner was standing up here, so I guess I should feel really honored. Those of you who have had chemistry know that thermodynamics is an important part of the study of chemistry. It's the basis for my discussion. What drives a chemical reaction? What is the measure of spontaneity for a reaction? You may have recalled the first attempts were to discuss disorder as the reason for the reactions taking place spontaneously. In the first figure shown on the left, the connected bulb with gas molecules all in one side of the apparatus will result in the molecules being equally distributed or nearly so. However, it will never go back to the point where they all return to one side. Neither will people ski up and down the hill at the same time like that. If you had me for general chemistry, or if you had general chemistry 2 already, I should say, you recall that spontaneity was initially equated with disorder. And if that measure is the sole measure of spontaneity, this is what happens when iron rusts. Oxygen reacts with iron, makes the rust. Oxygen's a gas. Gases have more disorder. So that means we don't have disorder. We have more order. So it doesn't happen. We don't get rust. But we know we do. So doesn't iron rust? It does. And so we use this idea of Gibbs free energy as the comment for spontaneity, not just spontaneity itself, not disorder itself. That brings me to the point of today's discussion. If thermodynamics dictates spontaneity, we can't go past thermodynamically stable states and come back and repeat that process, can we? It might be time to watch that a little bit as I'm talking, just to see what's going on over there, and I hope it is. Just for a moment, I'll quickly see if it's stirring enough. And it is. It seems, if that's an indication, that we probably can spontaneously go from one state to another and back and forth. But I thought that was against the idea of thermodynamic stabilities, against this idea of Gibbs free energy. How do we get oscillating reactions like that one? In order to do that, a few conditions have to be met. A couple of them are that the mechanism of the reaction, something like this one here, has to be complex, a very complex mechanism. The second is it actually has to be something that's autocatalytic. You make something that catalyzes a step that's already happened. It makes the step happen again. It goes back and forth around in another. And the other is that system must be far from equilibrium. These are often called non-linear chemical dynamic systems. And so I guess I would conclude this idea by saying if your system is like the first one, where you're bouncing around the actual state of equilibrium, then the system is not. That system would be breaking the laws of thermodynamics. So we have to go with the idea that instead it must be this second case where we are very far from the condition of equilibrium, and we are really tending towards equilibrium by going back and forth, although the reaction does continue to go back and forth. And I want to thank you for allowing me to show you that reaction that isn't working as well as I hoped it would, but I think did occasionally do so. As it keeps going back and forth from colorless to red. And I hope you understand then that even though we can have a system like this, it does not break the laws of nature, which would say that you have to go to equilibrium, because these systems really are heading to equilibrium. Thank you.